Welcome to Dr. Mode's chemistry class. Today we're going to talk about stoichiometry and specifically the BCA method. The BCA method is mainly about making a mole table, where the B stands for the number of moles of each reactant and product before the reaction, how they change during the reaction, and the number of moles of each of them after the reaction. So why use the BCA method? Well, it's useful when you're asked multiple questions about a chemical reaction. So let's go through an example. The example I've chosen is the combustion of octane. And we're going to look at the case where you're given a gram amount for each reactant. The first step is to write a balanced chemical equation. And here is the result. As you can see, you need 2 moles of octane to react with 25 moles of oxygen gas to produce 16 moles of carbon dioxide gas and 18 moles of water vapor. In the second step, we are going to write the number of grams of each reactant underneath its formula in the reaction. We are just going to choose some amounts. So for octane, let's say that we have 250 grams, and the amount of oxygen is also limited to 900 grams. In step 3, we're going to need the molar masses of each reactant and each product, and we're going to write those under the reaction as well. For this example, I'm going to round the molar masses to the nearest whole number. So for octane, we find that it weighs 114 grams per 1 mole. Oxygen is 32 grams per mole. Carbon dioxide is 44 grams per mole. And water is 18 grams per mole. All right, now we're ready for step 4. Step 4 is where we construct the BCA table. The setup for the BCA table looks like this. It basically is like an addition or subtraction problem where we're doing it 4 times, once under each reactant and product. We're going to start filling out the BCA table by including the number of moles of each reactant and product. Before the reaction begins, the number of moles of each product is 0. We haven't produced any yet, so that's the easiest case. So we can insert a 0 here for the number of moles of carbon dioxide and a 0 for the number of moles of water. Calculating the number of moles of each reactant at the beginning of the reaction is pretty easy. We just take the number of grams of octane and the molar mass of octane, and we'll basically just be dividing them like so. So 250 divided by 114 will give you the number of moles of octane. We do the same thing for oxygen. If we start with 900 grams of oxygen, and its molar mass is 32 grams per mole, we'll just divide those two numbers to find the number of moles of oxygen. The next step is to insert those two numbers into the table in our B row. So here they are. The next part of the process is to determine the limiting reagent. This is the trickiest part of the whole process. So there are numerous ways you can do this. The way I've decided to do it here is to start with the number of moles of octane that we wrote in the table, which is 2.193 moles and to multiply by the mole ratio between the oxygen gas and the octane, which is 25:2, to figure out how many moles of oxygen gas would be required to fully react with the 2.193 moles of octane. Well, what I do is I compare this number to the number that I wrote down in the table, the 28.1225 moles. And what I find out is that I have a little bit extra oxygen, and that means that the octane is my limiting reagent. So since I determined that the octane was the limiting reagent, I'm going to use that number of moles, 2.193, to fill out the rest of the table. The number that I calculated on the previous slide, the negative 27.413 moles of oxygen, is how much will be consumed. So that is going to be my first number in the change column, and because it is consumed, it's gone down, so we put a negative in front of it. Now I can do arithmetic and take the 28 minus the 27 number to find that there are 0.712 moles of oxygen gas remaining after the reaction is over. The next thing is all of the octane will be consumed. So I can subtract that original number, the before amount of 2.193 moles. It's all gone, which means I have 0 moles of octane remaining after the reaction. We are going to continue to use our limiting reagent number of moles to figure out how much carbon dioxide and water is produced in the reaction. Also, we're going to use the coefficients of the balanced chemical equation to determine these numbers. So, for carbon dioxide, what we have to do is we have to multiply the mole ratio of 16/2 to figure out how many moles of carbon dioxide is produced. And then for water, it has a different coefficient in front, 18, so we'll multiply by 18/2 to figure out how many moles of water is produced in the reaction. We are going to insert these two amounts into our table as positive numbers because they are produced in the reaction, during the reaction, and when we add these to the original amounts of 0, we find the same numbers. Now that we have the BCA table filled out, we are ready to answer any stoichiometry question that is given to us about the chemical reaction. The first question we might be given is, what is the limiting reagent? Well, we've already determined that it was the octane, but you can tell from your BCA table that it is the reactant with 0 moles remaining at the end of the reaction. Also, we might be asked, what is in excess? So that is the reactant that has a positive number of moles remaining after the reaction, which is the oxygen in this case. We also might be asked, well, how much excess is there in grams? So what we would do is we would start with the number of moles of oxygen remaining in the reaction and just multiply by the molar mass. That would give us how many grams of oxygen remain after the reaction. Remember, we started with 900 grams and there's only 22 grams remaining. You might also be asked how much carbon dioxide was produced in this reaction. So we'll take the number of moles that is produced. We can multiply by the molar mass of carbon dioxide to figure out the number of grams of carbon dioxide produced. We can do the same thing for the amount of water that's produced. We can take the number of moles of water that we have in the table, multiply by the molar mass of water to figure out the number of grams of water that's produced in the reaction. Another question you might be asked is, what is the percent yield of one of the products that's produced? Remember, the percent yield is an experimental number divided by a theoretical number times 100 equals the percent yield. We've already calculated the theoretical yield on the previous slide. In this problem, I'm going to say that if you've gone into the lab and done an experiment and produced 325 grams of water, then what is your percent yield? Well, what we do is we'll take that as our experimental yield, so it goes on the top, 325, divided by our theoretical, 355.3, times 100, and we'll find that we have a 97.47% yield of water. I hope this helps you understand the BCA method, and if you like this video, please check out our other videos on this topic, and always please subscribe to our channel, like, and share the video. Thanks.